Here are some examples from day 28. In day 28, we're dealing with long division, synthetic division, and then like in this problem, what they call synthetic substitution. Here what we're using is remainder theorem. Synthetic division can be used for two things. One could be to divide polynomials, but the other thing could be to evaluate polynomials. So what I'm going to do in this problem is, I'm going to come up with a shorter way to figure out what would happen if I were to get a -1 and substitute it for each of these x's and then evaluate and then simplify. Instead of having to actually do it the long way, there is a shorter way. So the number I want to plug in is -1. And I'm plugging it into a third-degree polynomial. In a third-degree polynomial, I would need 4 numbers, and I do have 4 numbers. The numbers in front are 6, -10, 37, and -106. So those are the numbers I'm going to use. Now, synthetic division, the way it works is it's a sequence of add, multiply, add, multiply, add, multiply, where you're going to add straight down. 6 plus 0 is 6, so the 6 basically just drops beneath the line. And then in order to get back above the line, I need to multiply, but every time I multiply, it's going to be with the input, the number that I plugged in, which is -1. So 6 times -1 is -6. To get back beneath the line, I add, which is -16. I'm going to keep on doing this, and eventually my output, the number I'm looking for, is going to end up here beneath the line in the last column. So -16 times -1 is 16. If I add there, I get 53. 53 times -1 is -53, and then once I add, I get -159. If I were to plug in a -1 into this polynomial, I would get -159. Okay, here what would happen if I plugged in a -3 into this polynomial? Well, I'm plugging in a -3. But this is a third-degree polynomial, which means I'm supposed to have 4 numbers, but something is missing. I have a third degree, which is the 2. I have a second degree, which in front there's a 1. I have a first degree, which is the -15, but here the constant is missing. So to hold the place, I need a 0. If I forget that 0, I will get it wrong, and eventually the number I'm looking for is down there at the end. That's the remainder, so that's why they call it remainder theorem. I drop the 2 by adding, multiply -6, add -5, multiply 15, add 0, multiply 0, add 0. So if I were to plug in a -3, what I would get at the end would be a 0. Okay, here use long division to find the quotient and the remainder, and enter the result in the form the dividend is equal to the divisor times the quotient plus the remainder. I don't know why this book wants you to input this as a product. That's not really the normal way that you express a quotient. I'll show you the correct way to do it, and then we'll just adapt it to how they want. But I'll show you how I would expect this on any type of an assessment. So here I'm dividing by x squared plus 6, but on a second degree polynomial, I need 3 terms. When we're doing long division, we're going to include the variables in here, but what we're missing is a first degree. So I'm going to write x squared, but when it comes time to write x, since it's missing an x, I'm going to write plus 0x, and then plus 6. I'm dividing, the dividend is a 4th degree, so I need 5 terms, and upon closer inspection, what I'm missing in here is a 2nd degree. I don't have an x squared, so I'll write 9x to the 4th plus x to the 3rd, but when it comes time for the x squared, I'll write plus 0x squared minus 10x plus 71. The way long division works is it's also cyclical. Unlike synthetic division, which is add, multiply, add, multiply, add, multiply, this is a 3-step process, and the 3 steps are divide, multiply, subtract, divide, multiply, subtract, divide, multiply, subtract, and I keep on going until the degree of my remainder is less than the degree of my divisor. I'll show you what I mean. The first step is to divide. Every time that you divide, you only take into account the lead term. Here the lead terms are 9x to the 4th and x squared. 9x to the 4th divided by x squared is just 9x squared. So I'll come to my x squared column, and on top I'll put right 9x squared, right above the 0x squared. Now comes multiply. When I multiply, I'm going to distribute the 9x squared times each of the terms that are in the divisor. So 9x squared times x squared is 9x to the fourth. That's very important. These numbers should match up. 9x squared times 0x is really just 0. You don't have to write anything. You can leave this spot blank, but if you must write something, then write 0x to the third. Right? We're maintaining this illusion of columns. We have an x to the fourth column, an x to the third column, an x squared column, an x column, and then a constant. 9x squared times 6 is going to be plus 54x squared. That was multiplication. Now comes subtraction. The easiest way to do subtraction is to get all these terms that I just multiplied and change the sign. So negative, negative, negative. Once I subtract, the lead term should always cancel. And the remainder for now, is, anything minus 0 is itself. In effect, what happens is this x to the third just drops down. So I have x to the third. 0 minus 54 is negative 54x squared. And then I'm also going to go ahead and drop down the next column, which is negative 10x. So I have now finished one cycle. Currently, x to the third minus 54x squared minus 10x is my remainder. But the degree of that remainder is third degree. The divisor is second degree. Since the degree of the remainder is still greater than the degree of the divisor, I'm going to continue. So I'm going to divide again. When I divide, I only look at the lead terms. X to the third divided by x squared is just going to be x. So I come up to the next column and I write plus x. Now I distribute. X times x squared is x to the third. X times 0x is plus 0x squared. And x times 6 is plus 6x. Now when I subtract, I'm just going to change all the signs. Minus, minus, minus. The leads cancel. Negative 54 minus 0 is still negative 54x squared. Negative 10 minus 6 is negative 16x. And then finally, this plus 71 just drops down. So that was another cycle. And currently my remainder is quadratic, but so is my divisor. So I have to keep on going. But I also now know that since the degree of the remainder and the degree of the divisor are the same, I should only have one cycle left. This will be my last go-round. I divide the leads. Negative 54x squared divided by x squared is just negative 54. Negative 54 times x squared is negative 54x squared. Negative 54 times 0x is just plus 0x. You don't even need to write anything. And then negative 54 times 6 is negative 324. One more subtraction. The leads cancel. Negative 16 minus 0 is just negative 16x. And then I got to change my signs. So this became plus, this became minus, and this became plus. So 324 plus 71 is 395. So plus 395. So now the way that most books will write this quotient is that they'll write what I have on the top line, which is 9x squared plus x minus 54. And then they'll write a plus, but the remainder, which is negative 16x plus 395, gets written over the divisor, which was x squared plus 6. That's one way of writing it. Another way, which is acceptable, I'll accept it. Most places will expect you to write it the way I have it written up there. But another way that could be acceptable would be to just write the 9x squared plus x minus 54, and then just write r for remainder, and then negative 16x plus 395. That would be fine as well. Here, they want you to express it as a product, so we'll just adapt to how they would like it. X squared plus 6 is the divisor, and they want that times the quotient. My quotient was 9x squared plus x. They've already written the minus in the 54 for me, so I'll just write 54. And then they want minus the remainder, which was the 16, plus the 395. use long division again and enter the results in the form that they want it, which is as a product. So let's see here, my divisor is quadratic, so I need 3 terms, and I have 3 terms, so I'll write 1/2 x squared plus 27x plus 2. I'm dividing that by a cubic polynomial, so I need 4 terms. I'm missing a term here, and it looks like what I'm missing is a constant. So I have to make sure that when I get to that constant, I can't forget to write a 0 in its place. Now let's start. We start off by dividing. When you divide, you only divide the lead terms. X to the third divided by 1/2 x squared is going to be 2x. I'll line up with the x column and I'll write 2x. 1 divided by 1/2 is 2. Now I'll distribute. 2x times 1/2 x squared is going to be x to the third. That should always match up. 2x times 27x is plus 54x squared. 2x times 2 is plus 4x. Now I'm going to subtract, which causes me to change all the signs. Minus, minus, minus. The lead cancels out. 104 minus 54 is 50x squared. Negative 7214 minus 4 is negative 7218x. And then this plus 0 just drops. I'm done with one cycle, but the degree of my remainder is still the same as the degree of my divisor, so I have one more cycle to go. 50x squared divided by 1/2 x squared is going to be plus 100. 100 times 1/2 x squared is 50x squared. Those should match up. 100 times 27 is plus 2700 x, and then 100 times 2 is plus 200. Remember, for the subtraction, to change all the signs. Minus, minus, minus. The leads cancel. Negative 7218 minus 2700 is going to be negative 9918 x, and then minus 200. I should be writing this as 2x plus 100 plus negative 9918 x minus 200 over 1/2 x squared plus 27x plus 2. But they want me to write it as a product, so I have to adapt to them. So here goes the 2 plus 100. Now they have a plus here in the remainder, but I got a negative. So I'm going to have to write negative 9918 x minus 200. Determine whether the given binomial is a factor of the polynomial. Okay, so now we're going to use synthetic division. But the way that you can use synthetic division to test for factors is if you get a 0 remainder. We're looking at the remainder. We need to see if the remainder is 0, the answer is going to be yes. We have factors. If the remainder is not 0, the answer is no. So now, unlike when we used remainder theorem before for evaluation, you see where it says we're going to divide by x plus 5. Well, first of all, it has to be linear, which x plus 5 is linear. That's what's going to allow us to divide. But the number I'm going to plug into synthetic division is not going to be a 5. It's going to be what would happen if x plus 5 was 0. So the number I'm going to put in actually is going to be negative 5. That's a very common mistake, is that people make mistake the signs to plug in. So I'm going to put a negative 5 into synthetic division. I'm dividing a 4th degree polynomial, which means I should have 5 terms. There's a term that's missing, and it looks to be the quadratic one. So I'll put the 6, I'll put the 37, but now when it comes for the square, I'm going to put 0 in that place. Negative 173, negative 4. Now it's add, multiply, add, multiply, add, multiply. I'm going to look and see what number ends up here. If I end up with a 0, the answer is yes. I have a factor. If I don't, it's no. This is going to be important when we start solving polynomial equations later on in the year. Add 6, multiply negative 30, add 7, multiply negative 35, add negative 35, multiply positive 175, add 2, negative 10, negative 14. So since I didn't end up with a 0, I ended up with a negative 14 as a remainder, then this is not a factor. X plus 5 is not a factor. Okay, determine whether we have a factor, and then if so, find the remaining factors. Okay. So here I'm going to divide by x minus 6, which means remember if x minus 6 was 0, x would be 6. So I'm going to put a 6 in here. This is a third degree polynomial, so I need 4 terms, and I do have 4 terms. So I'm going to write out in front I have a 1, then I have a negative 20, then 132, then negative 288. I don't use any variables. And I'm looking to see what the remainder is going to be. Drop down the 1, multiply, I get 6. Add, I get negative 14. Multiply, I get negative 84. Add, I get 48. And multiply, that gives me positive 288. So I did end up with a 0 remainder. So that's the answer to the first question, is since I have a remainder of 0, this is a factor. Now, in order to find the remaining factors, I started off with a third degree polynomial. Every time I perform synthetic division, my result, my quotient, is going to be 1 degree lower. When it's synthetic division, it's 1 degree lower. So what's happening, I started off with the third degree. Down here, these numbers that represent the quotient would then be second degree. So if I took out the variables in order to perform synthetic division, if I were to bring the variables back, because this is quadratic, this 1 would be representing x squared, this 14 would be representing x, and the 48 would be the constant. So I could rewrite this polynomial as x squared minus 14x plus 48. So the question is, can that be factored? And we've done that in previous units. 1 times 48 is 48, adds up to negative 14. All the numbers that multiply to give me 48 are 1, 48, 2 and 24, 3 and 16, 4 and 12, 6 and 8. And in this case, in order to make it add up, they would all have to be negative. And the one that gives me negative 14 is the negative 6 and the negative 8. Because the lead number was 1, that means that this could be factored, and it would be x minus 6 and x minus 8. Those are the last remaining factors. X minus 6 was already a factor, but now it's because it shows up again, it would actually be a repeated factor. The volume of a rectangular prism whose dimensions are binomials with integer coefficients is modeled by the function v of x is equal to x to the third minus 12x squared plus 35x minus 24. Given that x minus 1 and x minus 8 are 2 of the dimensions, find the missing dimension of the prism. Okay, so if I were to just draw a picture so that you could visualize, here's your rectangular prism. One of the dimensions is x minus 1, another one is x minus 8, and then we're looking for this missing dimension. They tell us that the volume is x to the third minus 12x squared plus 35x minus 24. Well, we learned in geometry that the volume of a rectangular prism is length times width times height. So if I could rewrite this as a product, then each factor would be one of the dimensions. Well, they've already given me 2 of the dimensions, so we're missing 1 dimension. Let's just pretend like that dimension was the height. I could get that height by then dividing the volume by both the length and the width. So that's what I'm going to do. Because both of the dimensions are linear, I can use synthetic division. So let's start off with the x minus 1. If I were to divide by x minus 1, that would be a 1 in the synthetic division. This is a cubic polynomial, so 1, negative 12, 35, and negative 24. Drop the 1. 1 times 1 is 1. Add negative 11, multiply negative 11. Add 24, multiply 24, and then I get a 0. Now, I have to get a 0 here because they've already told me that these are factors. They've told me that these are dimensions, so if I'm not getting 0, I know I'm doing something wrong. Well, I started off with a cubic polynomial. I've now performed synthetic division once. So these numbers that I got as a quotient, 1, negative 11, and 24, represent a quadratic polynomial. If I were to rewrite this now, what's left is x squared minus 11x plus 24. But I can continue doing synthetic division because they've given me another factor. They said x minus 8 is also a dimension. So I'm not going to put in negative 8. I'm going to put in 8. And I'm going to use these quadratic numbers that I just got, 1, negative 11, and 24, to do synthetic division again. Drop the 1, multiply, get 8, negative 3. 8 times negative 3 is negative 24, and then I get a 0. So up here, these numbers were third degree. Then these numbers here were second degree. So the numbers that I just got as a result are first degree. These are linear. And if I were to bring back the variables now, that would be 1x minus 3, which is just x minus 3. That's the last missing dimension, is x minus 3.